Hi, my name is Boon Peng. In this video, I will present our paper titled Cut-Paste Consistency Learning for Semi-Supervised Lesion Segmentation. Lesion segmentation is an important task in medical imaging. Broadly speaking, lesion is any damage or abnormal region usually caused by disease or trauma. Therefore, segmentation of the lesion boundary is essential to identify and assess the progression of diseases. Compared to organ segmentation, which focuses on well-defined structures such as livers or lungs, lesion segmentation deals with objects with larger structural variation. As a motivating example, consider the task of segmenting optic discs and soft exudate from color fundus images. Optic disc segmentation, as shown in the first row, is similar to organ segmentation, where each image can only contain one optic disc and its shape and size generally have smaller variation across different images. On the other hand, lesions such as soft exudate, as shown in the bottom row, have vastly different shape, size, and texture. Furthermore, they tend to be much smaller and scattered throughout the retinal tissues. This makes it very challenging and costly for the data annotation process, as greater care must be taken to inspect each lesion carefully. Approaches such as semi-supervised learning present an attractive solution to reduce the annotation cost. In this work, we propose a simple semi-supervised learning method for lesion segmentation based on the ideas of cut-paste augmentation and consistency regularization. We refer to the proposed method as cut-paste consistency learning. Starting with an image mask pair from the label dataset, foreground objects are extracted from the label image, which is then transformed and pasted onto an unlabeled image. This creates a partially labeled sample in which standard segmentation laws such as cross-entropy can be applied. Due to the sparsity of lesion distribution, it is reasonable to consider the region outside of the pasted region as lesion-free background. To further improve the robustness and rectify the rare cases of false negatives in the background, a regularization term is added to the unlabeled loss. This regularization term maximizes the consistency between the background prediction and background targets given by a target network. The background predictions and targets are obtained through masking with the inverted mask, while the target network can either be an exact copy or exponential moving average version of the main segmentation network. By combining the segmentation and background consistency loss, we arrive at the overall loss term for the unlabeled data. This loss is jointly optimized with the fully labeled loss in a semi-supervised learning setup. We perform benchmarks on two publicly available datasets and compare against prior semi-supervised learning methods. The first dataset I treat is a collection of color fundus photographs with 4 lesion segmentation tasks. In this dataset, our proposed method achieves the best performance in terms of average AUC PR score across the 4 segmentation tasks. The second dataset, CTICH, is a brain CT scans dataset for intracranial hemorrhage segmentation. We simulate semi-supervised settings by dividing the training samples into different labeled and unlabeled splits. Here, our method consistently achieves good segmentation results, especially at a lower data regime. In summary, we introduce a simple but effective semi-supervised learning method for lesion segmentation. We believe this method can also be applied to other domains that involve segmentation of small irregular objects. For more details and results, please refer to our paper. Thank you.